Thank you so much for inviting me and having me here. Some of you know that I was actually born in Taiwan, in Tainan, but I was transplanted to the U.S. when I was 3 years old, and actually this is only my third time back, so it's really a thrill to be back and to be among all your other friends here, and I'm excited to give you a little bit of a feel of what we do at my lab at Massachusetts General Hospital. So the two speeches you heard from both Robert and CT really tie into what I'm going to talk about, which is really nice because don't you hate it when your presentation completely conflicts with the previous one, but mine doesn't, so that's good. The lab at Mass General Hospital has been there for 50 years. It was started by a gentleman named Octo Barnett, very famous medical informatics professor who was one of the founding fathers. And what I'm going to talk about today is a little bit about why digital health. How is that different than other types of technology we've experienced? What do I mean by taking a full stack approach to solving digital health? And then I want to go through a brief review of some representative topics and projects in my lab. I've had the privilege of working with some wonderful faculty and researchers, and then take some questions at the end. So my question to you is digital health the same thing as high tech? What do you think? Is it the same thing as high tech? Okay, so to answer that question, I'm going to start off with this slide. So this quote by Atul Gawande says, "The history of American agriculture suggests that you can have transformation without a master plan, without knowing all the answers up front." So what this graph shows you here is the percent of disposable income spent on food in the United States between 1960 and 2011. And you'll see that it goes down from about 18% now to about 10 to 12%. So that's really a dramatic decline in what people spend for food, right? Now, contrast this with healthcare as a percentage of GDP. So there are a couple of different countries here represented, but here's the United States, and you can see it's trending up, and over the last 7 to 8 years, it's trending up even faster, right? So very different than what we see in the food business. Now you would say, well, it's trending up because we're doing better, we're doing a lot of good, but in fact, if you look at life expectancy overall, it's pretty flat in the US, and in the US it's certainly not the best, and arguably in the last year, there's been some data showing that life expectancy is actually taking a turn downward in spite of all that we're spending. And so if you look at food costs, USA spends very small amount of their income on food compared with the rest of the world. And food is good, it's safe, it's high quality, and we're spending less on it. So what's going on with healthcare? So the problem with healthcare is that we have a very complex healthcare system, right? And when you apply technology to complex systems that can be dysfunctional, you often amplify them, right? So things just get more expensive more quickly, right? You get MRIs that you may not need, you get overdiagnosis, you get overtreatment, you get new drugs that don't really work, but they're expensive and everybody uses them. And so you amplify this trend and you don't correct it. So I would argue that digital health is about correcting that trend, right? It's not just about high technology, it's about applying techniques that may be high tech or low tech, right? But it's about information, digitalization of information to improve health. We're talking about solutions that can increase efficiency and decrease costs while preserving or improving outcomes. And finally, we're looking at innovation that what I would call would democratize access to good health. So it isn't, frankly, just in the hands of doctors, right? I'm an internist myself. I see patients once a week in primary care, and I know that patients count on me to help them make the diagnosis and have the treatment. But frankly, it would be great if there were systems that would allow patients to do that on their own, in large part. And right now, when they come in with their Google searches and information, it actually makes my job harder because a lot of the information that they pull off the internet isn't right. So how do we solve this? I would argue that we need to do something called a full stack approach, where you have to really think about tackling this at every level. Those of you who are engineers know what I mean when I say full stack. It's talking about the database, as well as that middle layer of algorithms and computation. And then finally, this UI, which for programs is a user interface, but for healthcare is really care delivery. And you can't forget that. You could do amazing things in these two levels, but if you don't figure out how to get it delivered to the point of care, it won't make a difference. So let me first talk about a project related to the database part of the stack called the Research Patient Data Registry, or the RPDR, and an I2B2 project which evolved from the RPDR. Sean Murphy is one of the lead investigators in this. So the Research Patient Data Registry is a system that allows you to get patient cohorts for clinical research. Because as we know, one of the hardest things to do is to get patients that you can actually do your research on. And what we've created is a very large-scale database of about 6.7 million patients from the Partners Healthcare System. That's Massachusetts General Hospital and 6 other hospitals. It has about 2.5 billion clinical facts in it. And the neat thing about it is investigators can explore complex queries without getting prior approval. They're pre-authorized because initially they can just do aggregate queries and no data at an individual level is given out. So you can explore all you like and just get basic numbers to understand whether the population that you're looking for is reasonable. And then once you are satisfied that you've got something that you want, you can then get IRB approved unmasking, where you have your protocol approved, and from that aggregate query you already have done, it'll unmask and show you all the detailed information about the patients, including demographics, visits, diagnoses, medications, labs, anything that you might need to do your study. This is what the interface looks like. So you can compose it from many categories of data, and in this case, some of this is actually genotypic data, and then some of this is actually diagnostic information. But you can run the query and you can see a breakdown by gender, by age, by race, the total number of patients. And this is what you see when you first do the query without having approval to get detailed data. So the impact of the RPDR, and this is from 2014, there are about 5,000 registered users. I think there are about 8,000 now over the last 12 years. And about 600 teams per year use it for research studies. In 2014, there were about 3,000 patient data sets that were retrieved covering 24.7 million patient records. And when we did a survey for investigators to find out whether the data was useful, about 43% said it was critical for their research and 42% said it was useful. And what that translated to was somewhere between $94 and $136 million of total research support at our hospitals was dependent on using this kind of database to get the data needed for studies. And besides the research, there were about 300 data marts that covered 80 million patients that were extracted to support hospital operations. So you can imagine that this kind of data set developed out of clinical processes, basically taking care of patients, has been really instrumental in going forward and doing new studies. Now the next step was to take the RPDR to something called Informatics for Integrating Biology in the Bedside, or I2B2. This was a project that was sponsored by the NIH, and really what it did was take the RPDR to the next level, where the data model and the software is used now to transform and organize this person-oriented clinical data in a way that you can integrate other data, such as trials data and genotypic data, so that people could do genomics clinical research. It's open source software, and it's an application framework, so anybody can actually extend I2B2 for new analytical needs or workflow needs. This is the URL if you want to look for the software itself. And if you look on the website, there are community software modules. So there are different projects going on all the time at different locations. Something here called loyalty cohorts to try to connect physicians with who their patients are. You'd be amazed at how hard it is to find that out. But any kind of new technology, new analysis tools can be created to be plugged into I2B2, so that if you're running I2B2 at your institution, you can basically leverage other people's work. So the reach of I2B2, it's being used at over 50 academic institutions in the US. Here are a couple of the examples. At over 12 institutions internationally, and then at several healthcare companies like Kaiser, GE, or Johnson & Johnson. So it's really had a major impact across the globe. One of the main things that we do with the RPDR is to do feature extraction from the electronic health record, because one of the problems with the data in the clinical systems is that the diagnoses aren't necessarily accurate. So if you go into any classic electronic health record and say, give me all the patients with diabetes, you'll find out that probably 40% don't have diabetes at all. They have diabetes because somebody checked off a box saying, I'm going to bill for diabetes at this visit. So what we do is curate disease algorithms and therefore get good disease sets out of it. And what happens is the first step is creating a gold standard training set for the disease, and then identify which disease features from electronic records are those that would help one confirm that disease. And then you can develop some classification algorithms for those features, and finally apply the algorithm and assign a probability to any given patient of actually having that disease phenotype. So when you do that, you can start to have curated diseases so that when an investigator comes in and says, you know, I need diabetes type 2 in patients over 50, you can actually get a set of patients who meet those criteria. So some of the ongoing activities in this arena are around pharmacosurveillance, using the database to help predict some of the side effects that medications may not have been, people who initially designed the trials may not have even realized are happening. So for example, I don't know if you remember the whole Vioxx issue with these COX-2 inhibitors causing cardiovascular effects. When that came out, we went back to the RPDR, it was early on in the database, and we ran some queries, and in fact, you could see the correlation between people taking that medication and people having cardiovascular events. So you can use these large-scale databases to help find those types of events that you otherwise wouldn't be able to detect earlier than usual. There are also there's some work on high-throughput patient cohort selection with distributed federated queries. So instead of querying only your own large-scale database, you can actually send the query out across different sites across the US or the globe and pull back data sets that are across different institutions. And then finally, there's work going on in classifying similar patients, because when you can do that, you can optimize diagnostic and treatment pathways and help predict outcomes for your individual patient. As you know, clinical trials are limited because they are very selective when they do the trial. And when you see a real patient, oftentimes you're better off trying to find other patients who are very similar to them in order to decide how to treat them. All right, so that's the database layer. I'm going to go on to the next layer, which is diagnosis, and talk about an application called DXplain that's been developed in the lab over the last about 50 years. It's a diagnostic decision support tool that lets you put in findings and get a differential diagnosis.